In the previous lecture, we introduced the Bohr model, which successfully predicted the energy eigenvalues of the hydrogen atom. The problems with the Bohr model still persist. One is the origin of the quantization of angular momentum, which led to the quantization of energy, was not very clear. And secondly, the Bohr model painted a naive picture of the electron moving in fixed predetermined orbitals with fixed distance between the electron and the proton. And this in fact is naive because in the real world the electrons do not move in such a well predicted orbitals. And to have a better understanding of what's really going on inside the hydrogen atom, we need to go to the new quantum mechanics, which starts with the Schrodinger's equation, and we use the Schrodinger's equation to solve for the wave function of the electron moving at in the inference of a proton. And the solution to the wave equation will then give us desired results such as the quantization of energy and the angular momentum. And we also have a better understanding, better picture of how the electron actually behaves in the vicinity of a proton. So again, the quantization, the origin of the quantization of momentum, of angular momentum and energy will be addressed. And what we get as far as the picture of the electron moving inside the hydrogen atom is, instead of a well-defined orbital, we have what's called probability wave, as we saw in the previous chapter. The electrons will have a probability to be found in a certain region in space, but it does not have a fixed distance measured from the nucleus anymore. And we will get the same energy level and quantization of angular momentum, but again, a very different picture, no fixed radius. So let's take a look at how we can solve the Schrodinger's equation for the hydrogen atom. To do so, we first need to refresh our memories about the coordinate system to be used, the desirable coordinate system to be used here, which is the spherical coordinate system. Why is that? Because the Coulomb potential goes like 1 over r. It's not easy to express in terms of x, y, z, because then you have to go r equals the square root of x squared plus y squared plus z squared. It's not as easy as just 1 over r if you express the Coulomb potential in coordinate system. This is a spherically symmetrical potential, or we call it centrally symmetrical potential, and therefore it's easier to use the coordinate system, which is naturally reflective of its symmetry, which is the spherical coordinate system. So in a spherical coordinate system, we have the z-axis, xy axis, and r is the vector pointing from the center of the system to the point of interest. So we have a nucleus at the center of the coordinate system and the electron moving around it. As a good approximation, we say the nucleus is fixed because it's far more massive than the electron. So how do you describe the position vector of this electron? Well, we have 3 coordinates in the spherical coordinate. One is r, the distance from the nucleus to the electron. Another one is theta, measured from the z-axis. Theta ranges from 0 to pi as you turn around all the way from here to there. And another vector, another angle is phi. When you project this vector r onto the xy plane, it makes an angle phi with the x-axis, and this phi can turn around between 0 and 2 pi. So that is the spherical coordinate. So we need to transfer from the Cartesian coordinate system to the spherical coordinate system. And here is how we transfer. X equals r sine theta sine cosine phi, for example. What is x? This is x, right? This is from here to there. This is x. So if I draw it, this would be x. Okay, to get x, well, I start from r. This angle is theta. Okay, so I take r times sine theta. Remember, this angle is 90 degrees. Okay, times sine theta will give me this length. Then times cosine phi, don't I get x? Right, so that's one example. And you can get y similarly. And z is r cosine theta. That's very easy. From here to there, that is z. Okay, that is just r times cosine theta, as we saw in your math class. And again, these are the ranges for the variables r, theta, phi. And in the Schrodinger's equation, we have a Laplace operator, gradient squared. This is its expression in the Cartesian coordinate system, x, y, z. And we need to rewrite it in spherical coordinate. So how does one do that? Well, it's a little tedious, but it can be done. What you do is using the chain rule, okay? Partial x, for example. How do you write it in terms of partial r, partial phi, and partial theta? use the chain rule. Okay, for example, partial x equals partial r, then partial r partial x plus partial theta, and then plus partial theta times partial theta over partial x, and so on. So, and this is just the first derivative. Now you have to do another derivative using the chain rule one more time. It's a little tedious, but after you did that, this is what you're going to get. I'm sure you have seen it in your math class, multidimensional calculus. So this is, again, the expression for the Laplace operator in the spherical coordinate. We need that in writing down the Schrodinger's equation. In the Schrodinger's equation, remember, this is a three-dimensional expression for the kinetic energy operator. Here's the potential energy, here's the total energy. Okay, and the solution to this Schrodinger's equation is the wave function psi. It is a function of the three-dimensional vector r, which is a function of r, theta, and phi. So we have these three variables. So we have a partial differential equation for the wave function. Remember, how did we solve the partial differential equation in the previous chapter when we went from 1D to 3D? We saw only one example, right? But that example was very illustrative because we went from one-dimensional infinite square well to a three-dimensional infinite square well, and the key to solving this problem, the three-dimensional case, was that we introduced what? The idea of separation of variables. The separation of variables means that we are going to write the wave function as the product of several wave functions, and each of these wave function in the product is a function of one variable only. So for example, psi of xyz was written as psi1x times psi2y times psi3z. Psi1 is a function of x only, psi2 is a function of y only, and so on. And we are going to resort to the same idea here, the separation of variables. And that is, we're going to separate this psi into the product of three functions. Again, the first function depends on what? On r, okay? That's called a radial wave function. And the next function depends on theta, and the next function depends on phi. That is the idea. Actually, we're going to do it in two steps, not in one gulp. We're going to separate r first from theta and phi from the angles, and then we're going to separate theta and phi within the angular wave function. So let's do that. Okay. So you see here, I wrote psi in terms of product of two functions. This is the radial part of the wave function, which depends only on the distance r from the proton to the electron. And then you have another function which depends on the two angular variables, theta and phi. And let us plug this expression into the Schrodinger's equation, and all these three terms refer to the Laplace operator in the spherical coordinates. So I'm just copying that. Here is the first term in the Laplace operator in the spherical coordinate system. And remember, this psi is now r times y. Y does not depend on r, and in the first term in the Laplace operator, there is only derivative with respect to r, so y, this function y, does not have to undergo any differentiation. We just take it out. What's left is r, this radial function r, and you only need to do a straight derivative instead of a partial derivative because r only depends on one variable, the radial variable. That's that. The next two derivatives, one has to do with theta, another has to do with phi, okay? Because y depends on both theta and phi, you have to use partial derivative here. And you notice that both of these terms depend on r, but in a very simple way. It goes like 1 over r squared and 1 over r squared. And this is the next term in the Schrodinger's equation. It's just u times psi. Psi itself is the product of y and r here, just like what I wrote here. The other side is e times psi. Psi is again y times r. And I have used a red color to highlight the dependency on r. This depends only on r, the radius. This only depends on r, the radius. No angular dependency on either term. And then what did I do next? I factored out the common factor 1 over r squared from here, okay? And this is what's left. I just, copied from here to there. Copied from here to there, and took out this 1 over r squared, and moved this u term to the other side. That's harmless. And then once I did that, what I also did was I divided everything by y, the angular part of the wave function. Why did I want to do that? Because if I did that, then there is no y here, so the first term would depend only on what? On the radius r, right? And the next term, there will be, if I divide it by y, there will be a 1 over y here and a 1 over y here, representing this term and that term, right? And then those two terms I already combined. There is a y here, there's a y here, but I just divided it off. So the nice thing about dividing this by y, the angular wave function, is that I will arrive at this term and this term with no theta and phi dependency. Okay, with no theta and phi dependency. The only part of the equation which depends on theta and phi is this green part in the bracket. This green part in the bracket depends on theta and phi. All right. I argue then that this green part itself must equal to a constant. In other words, it should not depend on theta and phi. This whole expression inside the bracket must be a constant. Why is that true? Well, look, this is the only part of the equation that depends on theta and phi. Now let's suppose theta and phi changes. I want to argue that even if theta and phi changes, the expression should remain a constant. Why? Because if it's not a constant, then look, everything else depends only on r, right? If I fix r and change only theta and phi, then the black part should not change, this black part should not change. But if this part changes as you change theta and phi, then you're going to have a problem, because how come I only vary this part and yet the equation remains valid for those values that are unchanged, right? So therefore, it is clear that this function, the green part of the equation, should be a constant all by itself. And we call that constant negative lambda. We give it a name, we call it negative lambda. This means that this equation now separates into two equations. One is, you have this. This green part equals negative lambda. And since the green part equal to negative lambda, as you move this term to the other side, shouldn't that also be equal to negative lambda? Don't forget to move that r squared over, right? Because the two sides must be equal to each other. So basically just solve for the green part, move everything else to the other side. Both to the left and right hand side will equal to negative lambda, right? The result is that we have separated our equation into two. One has to do with only the radial part of the wave function. The other has to do with only the angular part of the wave function. And that is in the next page. So as promised, we have broken down the equation into the radial part of the wave function and the angular part. They both have a constant lambda in it, the same constant. And I'm going to deal with the angular part first. Now if you take a closer look, you'll find that a radial part of the wave function depends on the radial part, depends on the radial expression for the potential energy U. So if it's not a Coulomb potential, the behavior of this R, the function R, will be different. But the angular part has nothing to do with U. Okay? And therefore, the angular part should be the same for all wave functions in a spherical coordinate system, as long as the potential itself is isotropic, which means the potential does not depend on the angles. If the potential depends on angle theta and phi, then you haven't really separated theta and phi from R. So this is quite universal. We're not just getting it for the Coulomb potential for the hydrogen atom. We're getting it for any isotropic potential or centrally symmetrical potential. And let's try to solve this partial differential equation, the angular part. And we need to do the same thing here. Continue the process of separating variables. We're going to separate the theta and phi variables from each other out of this equation. So we break this equation down into two more equations. One for theta, one for phi. And the idea is exactly the same. We rewrite this function y into the product of two. This depends on theta, this depends on phi. Okay, so I use the capital letter theta for the function of theta, capital letter phi for the function of phi. And then I take this product, plug into here. The first term, I only have to take derivative with respect to this function, theta function, because phi has nothing to do with partial theta, so I take it out, right? I take it out. I use the blue letter for phi. And the next part, I only take derivatives to phi, and therefore theta comes out. It's just a constant. It comes out. And then the next one, lambda y is theta times phi, right here. So that's equal to 0. So these two are equivalent. How do I separate these two functions, theta and phi? Well, I use the same idea. I divide everything by what? By phi. So this term will have no phi dependency here. This term will have no phi dependency. Again, I have condensed the phi dependent part of this equation onto only this little term here. Okay, this little term here. And the argument is now the same as before. This part is the only part that depends on the variable phi. So therefore, it should really not depend on variable phi at all, because if I change phi and this thing changes, that's going to ruin the equation, because I can choose not to change the angle theta. So nothing else changes, so this part cannot change either, even though you change the angle phi, right? So therefore, this should be a constant as well. And this constant, I also give it a name and call it negative nu. Okay, negative nu. And therefore, theta has been separated from phi. Or phi has been separated from theta. So I let this equal to nu, and the rest of the equation move to the other side is also equal to nu. And now I have two equations out of the angular part, one for theta, one for phi, and this is what I have. So I have the equation for phi here, and the equation for theta here, after the separation of variables from each other, and both has a constant nu in it. And also there is a constant lambda coming from the initial separation of the radius r out of the equation. So I have two constants, lambda and nu. And which equation you want to tackle first? Well, clearly this one is the easy one out, right? So let's worry about this one first. This one is quite simple to solve. It says that the second derivative of this function phi is equal to a constant times the function itself. And here's the general solution to this equation. E to the positive negative I square root of nu times phi. Now, if nu is a positive number, then the square root of nu is a real number, and you get e to the plus or minus I times a real number times phi. That's sine or cosine. Right? And if nu is a negative number, then the square root of nu is an imaginary number with an I by itself, so you just get an exponential function, e to the positive negative something times phi. But what do you think nu should be equal to? Well, the argument for this function is the angle phi. The angle phi ranges between 0 and 2 pi, as we saw in the first plot. Let's go back to that plot again. Here. This is the angle phi. We take that vector r, we project onto the xy plane. It casts a shadow on the xy plane. Okay, this shadow makes an angle phi with the positive x-axis. I start from phi equals 0. I can turn around all the way to 2 pi. When you turn to 2 pi, the vector comes back to itself. Therefore, whatever function that we get for the angle phi must be periodic with a period of 2 pi, which means when you add 2 pi to this angle phi, the wave function should what? Should go back to itself, right? Because we came back to the same spot. It has to be a periodic function. Now, what happens when you add a 2 pi to this angle phi? Let's see here. I just added an angle 2 pi here, 2 phi. I can factor out this and that into two different exponentials. Here is the first one. The first one is just before. And here you have the second one, this extra factor when you add 2 pi to the wave function. But this extra factor should be equal to 1, right? Because, you know, the wave function should go back to itself after you add the angle 2 pi to the angle phi. And that means, again, this is equal to 1, which means the coefficient here, plus or minus 2 pi square root of nu I, should be equal to what? Should be equal to 2 pi times I times a integer m. Okay? Because e to the I times 2 pi, that equals 1. That equals 1. And I multiply m times, that's still 1. But this m has to be an integer. Okay? This m replaces the square root of nu. See that? And therefore, the square root of nu cannot be just anything else. It must be an integer m, a positive integer, an integer m. Well, in fact, m doesn't have to be positive, because if you take m equal to negative 2, that still is valid. Okay, so plus or minus m, I should say, plus or minus m. So m itself can be negative. So it's 0, plus or minus 1, plus or minus 2, and so on. Okay, and that in fact is our first quantum number. nu, this constant, cannot be just anything else. It must satisfy this. So therefore, plus or minus nu squared must be an integer m. This m is our first quantum number. And with that, the phi part of the wave function is solved. It is e to the plus or minus I m phi. This m again is an integer. This assures the periodicity of the wave function with a period of 2 pi. So you see, we have our first quantization condition in solving the three-dimensional Schrödinger's equation in centrally symmetrical potential. And the way we obtain this first quantization condition for m is just the same as the way we obtained any quantization condition before in the previous chapter, and is we try to satisfy what? The boundary conditions. Okay, that was how we obtained quantization for a bound state in one dimension in the previous chapter, remember? And here we have to satisfy also the boundary condition, except this boundary condition is the so-called periodic boundary condition for the angle phi. So here's our first glimpse into quantization of a three-dimensional case. Now, I have to tackle the next one, the hard part, this equation. I already know what this is, okay? Because this nu has to satisfy this, but it doesn't tell me yet how to solve the next equation. In other words, I have to solve it, and hopefully I can find lambda to satisfy certain quantization condition as well.